Hello, this video will cover week 2 of the course NCBM 0114. Remember, the purpose of this course is to get you familiar with the material that will be covered in your college credit class 1314, which is Pre-Cal 1. One of the things that we do a lot in 1314 is talk about and analyze functions, and not just analyze them, but graph them themselves and also use them to answer questions. What you see here on this first page are some of the most common parent functions. And the reason we refer to them as parent functions is because every other function is derived from them. You could also think of it as the function in its simplest form. So for example, for linear functions, we know the slope-intercept form, and we've been using this in the course already, is mx plus b. We know that m is the slope, and we know that b is the y-intercept. So for the parent function of a linear function, you can think of the slope being equal to 1 and the y-intercept being equal to 0. And so if we were to graph it, you could see here the origin is where the y-intercept happens, which happens to be the x-intercept as well. And because the slope is equal to 1 over 1, we will go 1 up, 1 to the right, 1 up, 1 to the right, and so on. So this is, I guess, the second one on your sheet, but we call it parent linear function. Now, because the equation for it is f of x equals x, we could also replace f of x with y. And if we do that, I'm just going to delete the slope here. Okay, so if I rewrite this form, instead of f of x, I replace it with a y, and I say y equals x. You can see that the input, or the independent variable, which is x, will always equal to the output, or the dependent variable, which is y. In other words, if I say if x is 2, y will also be 2. If x is -1, the y will be -1. And so that combination of points where the x and the y are equal to each other is what gives this function the name identity function. Why? Because the input is the same as the output. But right now, of course, it's good to know identity function, but also remember that it is the parent function for linear functions. And the equation is f of x equals x, or y equals x. You see arrows on both ends, and those arrows represent that the function does not have an endpoint. It keeps going and going and going. And that is because the domain for it, the x values that the function can take, is all real numbers. Now I'm going to move back to our first example that we have here. And for this example, we have what it's called the constant function. Now, the term constant, it refers to a number. So if we have f of x equals c, c being a number, or like we also call numbers, a constant. F of x equals to a number, or y equals to a number. Let's pretend that this number here is a 3. So then our equation will be something like y equals 3. In this case, it doesn't matter what our x value is. It could be negative, it could be 0, it could be positive. The y value will always be 3. And so all those points, once you put them together and you connect them with a line, that is what gives you a horizontal line. So we also call it constant because the function is constant. It's not increasing nor decreasing. It simply remains the same. Horizontal line, constant function, y equals to a number. Now let's move on to our next function here, and this is called the absolute value. And I like to remember the shape of it. It looks like a V shape, just for absolute value. Similar to quadratic, but if you notice quadratic, which is right next to it, it is more curvy. And so it does have that turning point, but we refer to that turn as a smooth turn. As opposed to the one with the absolute value, this is considered a sharp turn. When you guys take calculus, this becomes very, very important. Those smooth corners or turning points and those sharp corners. Now for the absolute value function, we have arrows on both ends indicating that the graph keeps going and going. The same applies to the quadratic function. Now for both of them, the domain, which is the x values that the function can take, is all real numbers. And actually, the domain is the same for the two functions that we discussed previously. So for this one, we have the same thing. Domain is all real numbers. So we use from negative infinity to positive infinity. Same for the constant function. The domain will be all real numbers from negative infinity to positive infinity. Now, once we get to the range, that's going to change slightly because the range is the set of all the outputs, in other words, the y values. And so here you could see the smallest y value is going to be a 0. And the largest, we don't know what it is. That's why we have arrows. So we're going to use the concept of positive infinity. Now here for 0, it is included. It's an actual point on the graph. So we will use bracket, square bracket. Same thing for here, the range of the y values. The smallest y value will be 0, included 0 to positive infinity. Now, this type of notation will be also covered in your class in 13-14. Now, let's move on to our next two functions, or parent functions. All of these functions are parent functions. And for this one, we have cubic. Here's the equation. Remember, this could also be y equals x to the third power. And so for that one, we see that x and y intercept at the origin. We have arrows as well. And to denote the domain, it will be all real numbers as well, from negative infinity to positive infinity. And for the range, same thing, from negative infinity to positive infinity. Anytime we use infinity or positive infinity, we do not use square brackets because we cannot say that infinity is included. Infinity is not a set number, it's just a concept that implies that the number is large, very large, and it keeps growing and growing, but you don't know exactly what number it will be. So no square brackets for infinity or negative infinity. The last parent function we have here, not that these are the only ones, we have plenty more. It's called a square root function, and it's also part of the family of radical functions. So in this case, this one is a little pickier because you cannot enter a negative number. If you were to enter that on your calculator, you will get an error message, or it will say something like no real solution. So because of that, we focus on the x values that go from 0 to infinity. Similar for our range values, they will be from 0 to infinity. And just to check, if we were to substitute this x here with a 0, the square root of 0 will be 0. And so that is what gives us this point here at the origin, 0, 0. So that is just a view of parent functions. As we go on the semester, in both classes, 01-14 and 13-14, we will dedicate more time to each function. We're going to spend some time discussing properties of the cubic function, of the quadratic, of the square root, absolute value, and of course, of linear functions. So now, in section 1.6, we discuss transformations, function transformations. And so that includes shifting, which could be vertically or horizontally. It also includes reflecting, which could be across the y-axis or across the x-axis. And we also include stretching and shrinking. And we do have two types of stretching and shrinking. One is vertical and the other one will be horizontal. So let's start with the easiest of all, which is the shifting of a function vertically. So the first thing I'm going to do is graph the parent function for this quadratic function, which is f of x equals x squared. If I was to form a table of values, and here I'm just going to choose some random x values. So for example, -2, -1, 0, 1, and 2. And I try to choose numbers that are on the positive side of 0 and on the negative side of 0, or the right or left side of 0. So in this case, f of -2. So if I substitute a -2 there, it will be -2 squared, which will give me +4. For -1 squared, that will give me +1. For 0 squared, that will give me 0. 1 squared, it will give me 1. And 2 squared, it will give me 4. So now what I'm going to do is plot the points that will come from -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. So we're going to plot those points here. 0, 0, 1, 1, 2, 4, -1, 1, and -2, 4. And what I'm going to do is connect them with a smooth curve, no straight lines. And that is the graph of the parent function, the one that we have here. Now, what this graph will do, part B, we see a number 1 here being added to the function, to the y value of the function. And so what that will cause is that all these points, you will add 1 to the y value. So the points will be transformed into -2, 5, -1, 2, because I'm adding a 1 to every single y value. This will be 0, 1. Here we'll have 1, 2. And here we'll have 2, 5. So let's go ahead and plot those points. -2, 5, -1, 2, 0, 1, 1, 2, 2, 5. And now I'm going to connect them with a smooth curve. And so what happened here, we had a vertical shift of 1 unit up. So to complete the statement here, fill in the blank, the graph of f of x plus c, in this case we were doing that +1, is the graph of f of x, the parent from here, shifted c units, in our case it was 1 unit, vertically. And I will vertically, I will say we will go up, or let's say upward. Your key for this is that we add 1 to every y value. That's how we found them. Now let's look at the next one. And here we have h of x is the same as x squared minus 1. So now let's complete the statement here. And so if we have that number and it's negative, we're going to subtract that to our y values. And so because of that, the graph will be shifted vertically, but in this case, it will be shifted downward. And so our points, and I'm going to go from the originals of the parent function. So I'm going to list them here. We're going to have -4, 3. Now we are subtracting a 1 from every y. Then we will have -1, 0. We'll have 0, -1. We'll have 1, 0. And we'll have 2, 3. Now, if you're not very good subtracting, you could just take a point and shift it 1 unit downward, and that would still work. And of course, we connect them. And of course, my drawing's not that pretty, but you're using a pencil, so yours should look better. Okay, and so there we have our 3 transformations. Parent functions in blue. The shifted upward is in red. The shifted downward is in purple. So let's move on to our next example. Well, let's answer this question. What is the difference in graph B and C when compared to the graph of the parent function? What do you think caused the difference? So let's say graph B is graph A shifted 1 unit upward. What caused the difference? Well, the +1. That's what caused the difference. Now, graph C is the graph, the same as the graph of A, but in this case, it was shifted 1 unit downward. And that was caused by that -1 that was right here. Now the next graph we're going to graph is the parent function for absolute value. So with our absolute value, if we create a table, anytime that you enter a positive number for your x value, your y value will also be positive because the absolute value is always positive. It measures the distance from 0 to that number. So the absolute value of 1 is just 1. Now, let's see what happens with 0. So with 0, the absolute value of 0, think of what is the distance from 0 to itself, and that will be 0. Now, if you have a negative number such as -1, you still have to think in terms of distance. And so distance is always positive, so that will be equal to +1. Now, in reality, what's happening with the absolute value is that the function looks at the input, and if it's negative, it will decide, should I leave it the same, or should I make it the opposite sign? So if it is negative, it needs to be turned into the opposite sign. So to do that, you could put a negative in front of it and multiply that by -2. So that's what will cause every absolute value input. If the input is negative, it will cause the output to be positive because of this negative that we have here. Okay, so let's graph this function. So absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2, absolute value of 3 is 3, and we could trace this line here. And remember, with the negative numbers, the absolute value of -1 is +1 because we're talking about distance. The absolute value of -2 of x equals -2 is +2. The absolute value of x equals -3 is +3. And so that's what gives us this line here. So that is the parent function. Now we're going to graph this one. And for that, it has a +2 that is being added not to the x, but to the y. So if we have all those points, I'm going to list them here. So let's say negative 2, comma 2, negative 1, comma 1, 0, comma 0, 1, comma 1, and 2, comma 2. So with our transformation, what we're going to do is add 2 to every y value. So add 2 to y. So this point now is going to be negative 2, comma 4. This one is going to be negative 1, comma 3. We're going to have 0, comma 2. And we're going to have 1, comma 3. And here we'll have 2, comma 4. So let's go ahead and plot those points. So negative 2, comma 4 goes here. Negative 1, comma 3 goes here. 0, comma 2 goes here. 1, comma 3 goes here. And 2, comma 4 is here. So let's see. We connect them, arrows, and you can see how each point was shifted 2 units up. So let's go to our last page for this lesson. Actually, we have 2 more, sorry. So we have this one, and now what we're going to cover is horizontal shifting. Actually, let's go back to the other one and write down that this covers vertical shifting. Some books refer to it as translation. So let's go to our page number 3, and let's just go ahead and establish that this is going to be covering the horizontal shifting or translation. Now, with vertical translation, it was very self-explanatory. If you add a number to the y, you move up. If you subtract a number from the y, you move down. With horizontal translation, we're going to have to think in the opposite way that we would be more inclined to think. And so that is counterintuitive. So the opposite of what your intuition might be telling you. So for example, how do you know if it is a vertical or a horizontal translation or shifting? Well, it depends on where the number is. Is it being added to the x directly, or is it being added or subtracted to the y? How do we know that? Well, parentheses in this case, they will matter. So this case tells me that I'm going to have a horizontal shift. If I had something like my previous equation, it would have been something like that, for example. You could see that 2 is not being added to the x directly because it's not in parentheses as the example that we have here. So now I need to get rid of this because we're going to need the space. Okay, so let's go ahead, and we already graphed the parent function for x squared, I believe. For this one, so it will be 0, 0, 1, 1, 2, 2 squared is 4. And then this one also reflects across the y-axis. Like that. Okay. Now, the one that I'm going to graph in blue, and actually let me just write down the points of the parent here. So negative 2, comma 4, negative 1, comma 1, 0, comma 0, 1, comma 1, and 2, comma 4. So the one in blue, remember I told you this is going to be counterintuitive. So we're adding a 2 to the x, but in fact what's going to happen is that the graph is going to be shifted to the left. I know you're wondering why. Well, that's why I told you, counterintuitive. There is a good explanation of it, but I would rather let your 1314 professor show you that. Now, if we have a negative number there, we're going to say that is going to move to the right. So let's see what we're going to do. So for the one in blue, instead of adding, we're going to be subtracting 2 from x. So our new points will be -4, 4, -3, 1, -2, 0. So I'm not doing anything to my y value. I'm just subtracting 2 from the x value. So 1 minus 2, -1. And then here we will have 0, 4. So we're going to plot those points. And we're going to connect them with the curve. And you could see that this was a shift to the left. Now let's go ahead and do the next one, the one to the right. And in this case, we're going to add 2 to every x. Now, if it's a horizontal shift, we need to do the change directly to the x. If it's a vertical shift, the change will be applied to the y. So we have this the points of our parent function. So if we add 2 to every x, we'll have -2 plus 2, so that will be 0. Let's just go ahead and copy the y values. Those are not going to change. Only our x values. So now -1 plus 2 will be a 1. 0 plus 2 will be a 2. 1 plus 2 will be a 3. 2 plus 2 will be a 4. So let's go ahead and plot them. So 0, 4, 1, 1, 2, 0, 3, 1, and 4, 4. And we connect them with a line. And that will give us the graph of the parent function shifted 2 units to the right. Remember, the equation had a negative there, but I told you it's counterintuitive. Okay, now let's use the square root function. So for that one, I'm going to give you some x values. So we're going to use 0, we're going to use 1, we're going to use 4, and we're going to use, let's use 9. And why did I use those? Well, because I chose them to my convenience. Because if y is the square root of x, and I want to say x is 0, the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. So from here, I will get the points 0, 0. And I'm talking about the parent function first. And then 1, 1, 4, 2, and 9, 3. So with the transformation that I have here, my points, and now this is going to be a horizontal transformation because the x is being subtracted, the 4 is being subtracted from the x directly. So imagine that it was in parentheses because it is inside the radical, inside the square root. So what we do, because it is counterintuitive, we have to add 4 to every x. So 0 plus 4, it will be 4. Nothing changes to the y. Let's copy all the y values. Okay, now our x values. So 1 plus 4, 5. 4 plus 4, 8. 9 plus 4, 13. And in fact, I will not be able to graph that, but it's okay. So let me graph the parent function first. It will be something like this. Oops. Not a very good graph. Okay, the next one, let's see, 4 comma 0, 5 comma 1, 8 comma 2, maybe here. And then we have it there. So that will be a shift 4 units to the right. Okay, now let's move on to our last and final page. So we already know how the parent function of the square root function looks like. Now we're going to go ahead and graph something that has two things. It has a vertical shift and it has a horizontal shift. So let's plot the points that I'm going to use. 0, 0, 1, 1, and 4, 2. So if I move 1 unit to the right, I'm going to add 1 to x. So that will be, my new point here will be 1 comma 0, 2 comma 1, and then 5 comma 2. My y values are the same, only my x values change. Now I'm going to apply the other change, which is this vertical shift, and that, well, let's write down here what will cause this -1. So it's going to be 1 unit to the right. Remember, the horizontal shift is counterintuitive. 1 unit to the right. Now that -2 vertical shifting is self-explanatory. So if it's negative, we're going to move down. So in this case, we're going to subtract 2 from y. So my new points, and I'm not going to go back to my parent function. I'm actually going to take the points from here. It's like I'm applying one transformation at a time. So now I need to subtract 2 from y. My x values will remain the same. So 0 minus 2, -2. 1 minus 2, -1. 2 minus 2, 0. So now the points of the final transformation are the ones that I have circled there, the ones in blue. So let's go ahead and plot them. So we have 1 comma -2. We have 2 comma -1. And we have 5 comma 0 right here. And so you get to see that this was a graph G was shifted 1 unit right. Remember, the horizontal transformation is counterintuitive, and 2 units down. And that is the answer for that. Now the next graph here, it's the cubic function, parent function. So I'm going to write down some points. -2 comma -8. And that is if we raise -2 to the third power, or -2 times -2 times -2. It will give us -8. Let's use -1 comma -1. Let's use 0 comma 0. And let's use 1 comma 1 and 2 comma 8. These values come from raising the number to the third power, or multiplying it by itself 3 times. So again, we have 2 transformations first. Let's deal with this horizontal one. So we have a +1. In reality, that means 1 unit left. So what we need to do is subtract 1 from every x. So our new points will be -3, -8, -2, -1, -1, 0. Actually, I'm going to write the points here. -3, -8, -2, -1, -1, 0. And then from here, 1 minus 1, that will give me a 0, 0, 1. And then 2 minus 1, and that would be 1, 8. Okay, now let's go ahead and do the vertical shift, and that will be moving 2 units down. So because of that, we need to subtract 2 from every y. And I'm going to use these points here that I have in red, not the ones from the parent function. Okay, now we're only making the change to the y, so let's just copy our x values because they're going to stay the same. So if I have 2 units down, we're going to be subtracting 2 from every y. So -8 minus 2, -10. -1 minus 2, -3. 0 minus 2, -2. 1 minus 2, -1. And 8 minus 2, 6. Now I'm going to go ahead and plot all of those. And so actually, I did not plot the parent function, the one with these points in black. So let's do that. 0, 0, 1, 1, 2, 8, -1, -1, and -2, -8. It's like somewhere over here. Okay, so we have our graph there. And of course, we have the arrows. Now, I'm going to plot the transformation in green. So we have -3, -10. I cannot graph that one, but I can graph the next one, which is -2, -3 is here. Then we have -1, -2. Then we have 0, -1 here. And then we have 1, 6 right here. I'm going to try to plot this one, -3, 10. All I got to do is kind of like go outside the Cartesian plane. And we have it right there. Now, it's not a very good picture, to be honest. Perhaps this one goes more like this. It goes down here. But you are free to use your calculator to look at the correct graphs. Now, last thing that we will cover from here is the reflections. Now, this is some functions could be reflected, and we could still not be able to tell if they were reflected or not. So think of the quadratic function, for example. I'm going to plot some of the points for the quadratic, 0, 0, 1, 1, 2, 4, and then we have them here at -1, 1, and -2, 4. Okay. Now, because this function, and you will learn this later on, is symmetric with respect to the y-axis, meaning that you can fold it on the y-axis and you will have the exact same shape on the left and the right side, because these y values repeat as long as the x value is the same number, but with the opposite sign, as you can see here, +2, -2, +1, -1. And so when that happens, if you were to reflect the points across the y-axis, you will just get the same graph. However, if we reflect it across the x-axis, such as this one, this will be a reflection across the x-axis. So if we do that, every single point, the y value will be multiplied by -1. So I want you to look at these numbers here and just think of the opposite number. So instead of +4, we put a -4. Let's copy the x values first because nothing is going to change with those. The y values, this one from 1 will go to -1. 0 will still be 0. Instead of 1, we're going to have -1. And instead of 4, we're going to have -4. So now if we plot those points, our graph will look like this. And there we have it, a reflection across the y-axis. So what did I do? I multiply every y value by -1. And that's how I got the new points that represent a reflection across the x-axis. And that is the end of the video. Well, actually, we do have to fill in the blank here. So let's see. So if your negative is outside of the function, that means that all the y values will be multiplied by a negative sign, causing a reflection about the x-axis. Now, if you have your negative inside the parentheses, that means all the x values will be multiplied by -1. And if you do that, that will cause a reflection about the y-axis. And that concludes the video. So thank you for watching.